So let's look at derivatives of exponential and logarithmic functions. You knew we had to find ways to get derivatives of more things than just polynomials. Yeah, all right, so that's all we did in chapter 10 is we learned how to find derivatives of things that can be written in polynomial form. But not everything is polynomial in nature. We just looked at things that are e raised to a power. That's an exponential function when your variable is in the exponent. It's an exponential function. We've also talked about logarithms. We have LOGs and we have LNs. So we need some rules to help us know how to differentiate those types of functions if we see them. So we're going to be building our arsenal of derivatives. Look at the box here. And remember that d over dx is the notation we use when we say we're finding the derivative with respect to x of e to the x. And this one is your fun little friend. You're going to like seeing this because look what the derivative is. The derivative of e to the x is e to the x. Whatever, it's itself. That's pretty darn easy, okay? Now, if the base is not e, maybe it's a different number like 5 to the x, okay? To differentiate, we will also keep that number to the x power, okay? That's going to be the same as what we had here. E to the x equals e to the x. So if I'm differentiating some number to the x, b to the x, it's going to be equal to b to the x. But notice what else we need. Times the natural log of whatever that base is. Now, think about it for a minute because really it's the same rule over here. The only difference is we don't have to put natural log of e with this because what is the natural log of e? 1, because the exponent on the e is a 1. So it cleaned up. That's why you don't see it here, but you got to make sure you don't forget it here if the base is something other than e. Now, on the natural log function, if we're finding the natural log of x, it differentiates as 1 over x. Now, there's a reason why we have to do that. Look at what happens if our base is something different than e, because it's the natural log of x with a base of e. If it's a different base, it's probably going to be written as log with whatever number goes there, okay? So it could be base 10, it could be base 7, and if we're taking the derivative of that, we still get the 1 over x, but notice you also have to have the 1 over the natural log of the base. Again, same thing here. We could put times 1 over the natural log of e, but we said the natural log of e is 1, 1 over 1 is 1. So this is just the cleaned up form of this. These you need to become very comfortable with. You're going to get to use these notes when you test so that you will remember those derivative formulas, but make sure you look back. Probably the more you use them, the more comfortable you're going to get with them, and you may not need to look back at your notes very much. All right, so here's what we're probably going to see is we're going to see several terms put together in a function. Most likely, a good many of them will be polynomial in nature, but now we may also see logarithms and we may see exponentials mixed in. And just like we did before, we will differentiate term by term. So as long as I have something in a plus sign, I can differentiate that term, move past the plus sign, and differentiate the next term. But keep in mind, we may end up needing to pay attention to rewriting a few things. If we see square roots in there, we'll have to rewrite them with fractional exponents. If we have something that has x to a power in a denominator, we'll have to rewrite it so we don't have a fraction. So let's see if we can take care of these. Look at this first one, and if we're finding the derivative of this function, look at the very first term. And the fact that there is a coefficient of 4 in front of e to the x, does that make it any harder to differentiate? No, because what are we going to have to do with the 4? we just keep it as a constant multiple or a scalar, right? It'll be 4 times whatever the derivative of e to the x is. So what's that going to be? The derivative of e to the x is e to the x. So it's 4 times e to the x plus, now can you differentiate 5x to the 4th? What does that become? 20x cubed. Very good. How do you differentiate minus 12x? Just becomes minus 12. We take the 1, that is the exponent on the x, pull it down, multiply it times the coefficient, and then when I subtract 1 off, it left me with x to the 0 power, and x to the 0 power is 1. And the derivative of a constant is always what? 0. So when I differentiate 46, I get 0. We're done. Not too bad. Let's look at number 2. We want to find the derivative of negative 7 e to the x plus 5 natural log of x plus 12x minus 35. So we got a little bit of everything in this one. What's going to be the derivative of negative 7 e to the x? Negative 7 e to the x. Those are our happy place when we see an e to the x that we have to differentiate. How do you think we differentiate 5 times the natural log of x? Excellent. So plus 5 times 1 over x, because we keep that constant multiple or that scalar 5, and then when you differentiate the natural log of x, it becomes 1 over x, plus, how do you differentiate 12x? It's just 12, and the derivative of negative 35 is 0. The only thing left to clean up here would simply be to go ahead and multiply 5 times 1 over x, and we'd have our negative 7 e to the x plus 5 over x plus 12 as our cleaned up finished derivative. Okay, so let's see what we have going on in this next one. We need to find the derivative of 4x cubed plus 2x squared minus 5x plus the natural log of x to the 5th plus e to the x. All right, lots of terms there. Let's go term by term. 4x cubed differentiates as?
12x squared.
Excellent. 12x squared. Plus, how do you differentiate 2x squared? 4x. Excellent. Minus 5x becomes a negative 5 when we differentiate it. Now, can you differentiate the natural log of x to the 5th? Here's where you better be careful. I cannot differentiate it until I first rewrite it. Do you remember what I told you you can do with that exponent if you're taking the natural log of something raised to a power? What did we just discuss a minute ago? Yes, we multiply exponents. That means we pull that exponent down in front and we think of this as 5 times the natural log of x. Now that looks like something I'm going to be able to take the derivative of. What's that going to become? Good. 5 times 1 over x, which we know from the previous problem is 5 over x. And then what's going to be the derivative of e to the x? Are we good? You just differentiated something that had 5 terms, and you had a little bit of everything in that. The only thing we haven't done yet is something with a radical, but I don't think you're going to have any trouble with those because we've been practicing those for a while. Okay, look at 4. We have y equals 10 to the x power minus e to the x plus 3 minus 5x. Now, this is the first time that I think we have seen an example where our base was not e raised to the x power. It's 10 to the x power. How are we going to differentiate that? Good. Remember, it's going to be 10 to the x, but we have to multiply it by what? ln of 10, the natural log of whatever the base is. Remember, they used b in the formula. In this case, b is 10. So 10 to the x differentiates as 10 to the x times the natural log of 10. All right, how are we going to differentiate minus e to the x plus 3 power? Well, remember we said e to the x power differentiates as e to the x power. Technically, what they've given you is something we should use the chain rule for. We're going to learn that in a couple of sections. They're kind of bad about this, putting some things in a little ahead of time. But what we would discover if we use the chain rule is we would end up with x plus 3 as the derivative of this exponent anyway. So it's just going to differentiate as itself, minus e to the x plus 3 power. Okay? Remember, e to the x differentiates as e to the x. So e to whatever exponent we see there is going to be how that differentiates. And then what's going to be my last term? Minus 5. Very good. So when we get to 11.4, we'll talk about where we would have a problem is if instead of x plus 3, if that exponent had been 3 times x, we would not have differentiated it as e to the 3x power. We're going to have another rule for that. But as long as it's x plus 3, we're fine. All right, look at number 5. We have y equals log base 7 of x plus 3x to the 5th minus 4 to the x power. Okay, so a couple of things in here where our base is not e, it's a different number. Let's see if you can tell me how we're going to differentiate log base 7 of x. Okay, is that, you said 1 over the natural log of 7, is that all we need? So if you look back at your rule, it's 1 over whatever followed the base, right? Which in this case is our x. So 1 over x times 1 over the natural log of the base, which is 7, right? Okay, so that's going to be how we differentiate the first term using the rule that we have at the beginning of this lesson. How do you differentiate 3x to the 5th? 15x to the 4th. Take that current exponent times 3, 5 times 3 is 15, and then take 1 off the original exponent. And now differentiate minus 4 to the x for me. So I know I'm going to have a minus what? 4 to the x power. Is that all I need? Times the natural log of 4. Very good. If my base is not e, I've got to make sure I take the natural log of the base.
Is it going to be negative or a positive 4 when you put it in ln?
It's going to be a positive 4. Okay, because what we're doing is we're subtracting all of this. Okay, so you could think of it with the parentheses there, but we really don't have to have the parentheses because they're all factors. So remember, without a parentheses, the only thing that the x is attached to, the exponent is attached to the 4. So that's why we're putting in a positive 4. If it was in parentheses, we would have something different, but you're not going to see that. So if we clean this up, and the reason we're not going to see that is we need a positive base. We're going to have 1 over x times the natural log of 7 plus 15x to the 4th minus 4 to the x power times the natural log of 4. All right, last page of examples to look at for this section. It says, given the function f of x equals 5e to the x plus 7, we want to find the equation of the line that's tangent to the graph of the function at x equals 0. Now, here's what is a little different, because we've done these problems, but the ones we've done were all polynomial. This one is exponential because it's 5e to the x power plus 7. So in order to get the equation of a tangent line, you guys told me a minute ago when we were reviewing, what do we need to find? We've got two important pieces of information we need. One thing we need to find is slope. How do I find the slope function for this particular equation? I have to do what? Find the derivative. So I'm going to find the derivative. How do I differentiate 5e to the x? It becomes what? 5e to the x. And then since my second term is plus 7, the derivative of 7 is 0. So I found my function that lets me find slope. And since I want to find the equation of the line tangent at the point x equals 0, I need to do what now? Well, I don't want to set it equal to 0, but I want to plug in 0 to this function. I want to know what is the slope at the point x equals 0. So if I have 5e to the 0 power, okay, what is anything raised to the 0 power equal?
1.
Excellent. 5 times 1 is 5. So here's what I know. The slope is 5 at the point x equals 0. Does that make sense? Okay, good deal. So even though it was exponential, we were still able to get a numerical value for slope. The worst thing that's going to happen here is it might be a slope that has an e in it. But remember, e is a number, so it's not a problem. It just means your equation for your tangent line might look a little funny to you. Now, we've got to find the y-coordinate, because remember, we need a point to go with this slope, and how do we do that? You're right. We're going to plug in 0 to the original function. That will tell us what the y value is at that point, right? So our original function was 5e to the x plus 7. So we're going to have 5e to the 0 plus 7. What's that going to be?
12.
Excellent. We have 5 plus 7, which is 12. That means the ordered pair that the tangent line and the original graph have in common is 0, 12. So now I've got a point and I've got a slope of 5. So my m was 5, my point is 0, 12. Do you remember the point slope form for an equation? Actually on this, do I even need point slope form, or did I find the y-intercept? I have the y-intercept, because if my x-coordinate's 0, this is my b. That's my y-intercept. So what's going to be my equation? Y equals?
5x plus 12.
You got it. Now, if it hadn't been the y-intercept, then we could plug into y minus y1 equals m times x minus x1, and then we could get it into slope-intercept form. But this is actually the equation for the tangent line.